is not very good. So this increases a lot the
Okay, that's
the overhead.
basically this will always be sent.
Yes,
So this is just a very short fireworks packet.
fireworks.
Where you basically say, okay, now I'm
Yeah,
setting
yeah,
the
yeah.
priority.
Okay,
Right.
yes, fireworks. I didn't.
If you did, here you know that only have 3 nodes, but
Mhm.
if you have like 20, the winner will have to be sending 1, 2, 3, 4, 5 pulses per second.
No. If you had 20, just send one. If
But
and
how
then
would
just-
they know that you win, that you won?
just because, like here, just because he reached the end of the tournament
No,
and he never heard
He has
a
to reach
reception.
the end of the tournament, so he has to send 20 pulses.
No.
You assume that every node has 1 bit. That's not true. What you've got is priorities. So
We have
20
priorities. We
will be 5
define.
bits.
It's the protocol defines. Okay, we have 10 priority bits, and that's fixed, no matter how many nodes you have.
Okay,
And
so
that
if you
defines-
have 20 priority levels, you need always to send 20.
No,
No.
no.
10 bits. 10 bits are 1,000.
10 bits are 1024 priority levels, right? It's the power of 2.
The
Of
examples
priority
here are
bits.
chosen that each has 1 bit.
Exactly. Here I've chosen these examples so that I would have different situations, but you can have with 3 priority bits. It's what I have here. You can have 8 priority
Eight
levels.
Okay.
Okay. And so with the number of priority bits, it raises exponentially.
But there are other protocols that work, like you mentioned.
Exactly. There are protocols that work
So
like you
not
said.
clear.
It's it's blackburst. Blackburst. Okay. Never.
No.
So it was 2 slides, okay? Not 2 more for you. So just as a summary of our main results that we've done in this part, so related directly to the MAC protocol, is that we have designed what we call WIDOM in a single broadcast domain. So we call this, it's just because we assume this, that all nodes can hear each other, what you were talking about. So we have designed it. We have said how we can choose the timeouts, how we can design this protocol. We have shown the working prototype implementation, and we have developed a schedulability analysis under that assumption, which is basically just changing a little bit the CAN analysis. So now what would be interesting is to obviously to have WIDOM working in multiple broadcast domains, so when not all nodes can hear each other. I tried to have a drawing of what could be here, but basically is that when a node transmits, not all nodes in the network can hear that transmission, can detect that transmission. And then for both single broadcast domains and multiple broadcast domains, we wanted to have an implementation that would have lower overhead, because this prototype implementation, it showed, yeah, it's possible, but it had a huge overhead. So we wanted to have something that would make this actually practical, not just showing that it can work, sort of work, something that would make it somewhat practical.
What would be sort of, just to give me a gut feeling, the switching times for switching the transceiver?
So I have a
from
slide
X?
about that
Okay.
later on. So what I've showed you until now was basically this, I hope. So what I'm just briefly going to talk about this, how we made this extension to multiple broadcast domains, and I'm going to show you about this implementation, and I'm going to show you just one line saying why, and I have those numbers there. Okay. So now, how did we did this extension? Again, not much detail, but the basic idea is to repropagate priority bits. So instead of just having the transmission of priority bits, now in our multiple broadcast domain, what we have is that we have bits are transmitted in 2 phases. One phase is where nodes transmit their own priority, and then another phase where nodes transmit whatever they heard in the first phase. And this is done for each priority bit, okay? What that basically amounts to is that each node will transmit priority bits, will propagate priority bits 2 hops away, okay? And so basically this will make enforce the priorities between 2 hop neighbors. What we had to solve, and that wouldn't work simply as the way we were doing it, is how we achieve this synchronization. So the first, we wanted to have this without any masters. So basically what we do is we retransmit the carrier pulse throughout the network as soon as it is detected. So if a node starts a tournament somewhere in the network, other nodes will basically immediately retransmit that over and over and over, okay? Arbitrarily through the whole network. Okay? You can think that this is not a very good idea, but it works, and it allows parallel transmission. It doesn't block the whole network. So yeah, it sort of works.
I was just thinking about, we have switching times in each node, sort of depending on the amount of
The overhead
duplicates.
duplicates basically.
I think that's interesting. So if you have a network with a diameter of say 20 hops, it does not mean that the overhead becomes 20 times bigger. You might think that you need
it's
to
just
propagate
twice.
the sync path, but it's only twice.
Yes, that's
So-
important to
What?
see.
No.
No,
The sync bit, if you want to propagate it from one end to the other end,
Yeah.
means first hop.
No, we don't have to wait. That's the thing. So the way we do this in the protocol, we encompass for 2 hop, let's say, desynchronization. So I should go back, right? We encompass for, let's say, the different notions of time in 2 hops distance, okay? So what we do is when we repropagate, and we account for this difference in a 2 hop region, and then we just continue repropagating, but we don't have to wait until the sync pulse goes throughout the network and then do the tournament. We just repropagate and do the tournament, and the tournament will happen, let's say, in parallel in different regions of the network, okay? Because it will just go further on.
Okay. So the error, if you look at one node in the network and another node in the network, and ask what is the error in the clocks, that will depend on the diameter.
Exactly.
That's true.
But in the protocol that doesn't matter, because we only do the priority bits 2 hops distance. So for us, it's only important the 2 hop distance difference, not from an arbitrary node to another arbitrary node in the network. We don't care
I was
about that.
just trying to construct a case where you have sort of 2 paths.
Yes.
Exactly.
And end up on the
That's
same.
the typical case, and we don't care because we are transmitting pulses. If they just
Yeah, and all I ever get is, because they are synchronized, wherever they meet, they will be at the same time zone. Assuming that the clock
Exactly.
per se is not true.
Exactly. So
The
yeah,
absolute clock
we
is-
thought about those
It's nifty.
those situations, and so far we think it works, and we have made experiments that show that it does work. So
So one quick question.
yes,
So I was just, why this 2 hop limit? Why this? Is it
Because
out of
it's
the
a-
blue, or-
no, 2 hops is as long as we want. It is as long as needed and as long as we want it. Because if we transmit the priorities more than 2 hops, we will make nodes that could transmit, not transmit. Do you understand that? I have
You
this.
want to get right the man in the middle between the
No,
2
I
hops.
understand.
Yes.
So, but then you're,
Yeah, basically this, I could show you that situation here. So we don't want to repropagate it more than 2 hops because in an entire network, we want to allow this, you see. This node, and this node, and this node are transmitting, let's say, in the same tournament. They were winners of the same tournament, okay? Why? Because we only repropagated 2 hops away. If we propagate priorities more than that, we wouldn't allow these nodes eventually receive, these
One-
nodes to
one and
transmit.
nine are particular to